Hello, all. 2 minutes, please wait. We will start, okay? Thank you.
Good evening, everyone. Am I audible?
Yes, you're audible.
Okay. So, good evening, everyone. So, today it is a demo class of our analog layout course. Before that, just want to give some basic introduction. So, you people came here to enter into the VLSI industry. It's a very beautiful industry in terms of salary wise and everything. This is an analog layout course where we will completely focus on only analog design related and layout related things. Op-amp, BGR, many other things, MOSFET, everything. So today will be the basic introduction class where I will teach you the how to do the what are the overview of analog layout, starting from the basics of layout to exam till last. What are the topics we will cover in the course, and meanwhile I will try to give some brief insight to make you people comfortable to understand what are the things you need to learn and everything. Okay, so eh, please confirm my screen is visible, right?
Yes, it is visible.
Thanks for confirming, Shobanish. So, just a second. So, what is analog layout flow? If I ask anyone what is analog layout flow, anyone can tell. Like first, let me tell you what is analog layout. You people might have know like all the chips. Like you people are using mobile phones or laptop or anything. So there, the chip, our chip. Basically, if I draw, let me draw. I will show you. So basically, suppose if you draw any Intel i5, i7 chip or Samsung Exynos chip or Qualcomm Snapdragon chip, if you find, you will find this is the suppose everyone is using nowadays a laptop, right? So suppose if I draw i5 chip, Intel i5 chip, how it will be? Like there is a IO outer side. This is a chip, and inside the chip there will be billions of transistors, right? Transistor means MOSFET. One, two, three. Like that, many MOS transistor is there, right? Like that, many transistor, and it should be connected properly. Suppose this is my everyone know inverter, right? So this is my two device, and two device should be connected. These are the routing, right? These are the wires. We will use metal wire to connect. So this need to connect using metal wire. So this is what analog layout. We will place the device and we will route, and we will verify. So in very simple term, what is analog layout? Basically, so I write down here. Place the devices. Do routing means connection. Routing as per the design. Then verify means DRC, LVS. You might not able to understand what is DRC, what is LVS. Don't worry, I will teach everything. DRC, LVS, all this. So these are the things we need to know. Place device, do the routing, and verify. So when we will, I will show you. Let me show you some analog. What is analog layout? How what we need to going to learn in this course. Suppose this is my inverter schematic, right? Now, if I go for this inverter schematic, right? If I open the layout of the schematic, so this will be the layout. It will looks like this. This is the layout looks. This is just a second. I will show you. So, there, NMOS PMOS is there, right? Okay. Yeah. So this is the PMOS, like above inverter PMOS, you know, and this is NMOS. So like that is this is the device, and we need to do the routing. There will be metal layers. There will be M1 metal. This is the M1 metal M2 layer. We need to do the routing. Then we need to run the DRC. So this is what very basics of analog layer. So now coming to the point. So we need to place. There I show you. I have shown you. Here what I am doing, placing the device over the screen like this. This black screen is substrate. Everyone knows fabrication related substrate and all. I will teach you in fabrication. This is I'm giving just brief overview. I think you people have idea what is P substrate or not. This black screen is P substrate, and these are the device. And over the substrate we will go for the fabrication. Okay. So now, what is the analog layout? It's slow. First, we will go for floor planning. For floor planning means we need to plan. We need to place the devices. Suppose if I have 4 or 5 devices. Suppose if I have, this is my schematic. Suppose this is my schematic. And so 4 devices. Suppose 4 devices are there. So these 4 devices I will place like this. 1, 2, 3, 4. And I need to route, basically connect them. That's called routing. So 4 devices I will place. So floor plan means I need to floor plan. Basically, when we build any building, our home or any our room, we need to first we do the planning, right? There we will do the my bed. This side will be window. This side will be my door. Like that, we need to floor plan, and we need to discuss our rough floor plan for the area estimation. For the floor plan, why we are doing for the rough area estimation. Like if I place 4 devices like that, if I show, then this much area will require. If I show you, then this much area. This is the x-axis, this is the y-axis, right? So x and y, this much area is required. So this is what floor planning. Now placement. After floor planning, if your floor plan approved by your lead, suppose you will reporting to manager or lead who is handling the project, you need to report show your manager or lead or designer team. Is this floor plan is correct or not? If we agree, then we will go for the final placement. While doing the final placement, what is placement? Placement means we need to place the devices. We need to place the devices. Like I will 1 device, 2 device, 3 device, 4 device. There can be thousands of devices. In Intel i5 chip, there will be billions of transistors. So we need to place the devices, and we need to go for there are some layout technique, matching, shielding and all. I will tell you those details. Just as of now, for the basic information, I am just placing. Then I need to clean the base DRC. DRC means design rule check. What is DRC? DRC, I'll tell you. DRC means design rule check. So in design rule check, what you need to do? Suppose is this is a one device. This is the top view of a device, right? This is poly. Suppose this is a poly. This is the top view of a device. And this is source well. This will be source well. And here is one more device. This is N P plus PMOS, so will be P plus, and it will be N plus, right? N plus diffusion. This is called N plus diffusion. So there will be some distance we need to maintain, like there will be some design rule. N plus to P plus distance. This distance would be, suppose in DRM, there will be 0.2. Or this poly to this poly distance should be 0.16. Like that, we need to maintain this distance. This is called base distance. So P plus to P plus or poly to poly distance, this distance we need to maintain. This is called base distance. We will, each and everything we will do in details. Then we will do the routing. Routing means we need to route the connection. Whatever connection is there, then we need to route them using metal layers, M1, M2, M5, M6, whatever possible metal layer, we need to route. There are some routing rules will be there. When we will do routing in details, I will tell you. Then LVS. LVS means layout versus schematic. What is layout versus schematic? LVS means layout. If people can note it down in the simple way. Layout versus schematic. So what is layout versus schematic? The number of devices in schematic, pins, devices, pins, instances, everything should be matched with the in the layout. Layout and schematic side should be same match. Layout versus schematic. If I do 2 match is there, this side it was five device, this side it should be 5 device. If this side 10 pins, this side also 10 pins should be. Okay? So this is called LVS. Layout versus schematic should be properly matched. There will be many errors, stamping error, property error, incorrect insert, incorrect nets. So we have to go through all these things. Okay. So now, then again DRC. Then I need to do that. Right. So what is the difference with base DRC? Base DRC means we need to maintain the DRC between base layers. There are base layers are there, right? We need to maintain the DRC. And what is base DRC? Here are the metal related DRC. All the metal related DRC we need to clear. So this is the again same floor plan. So what is the analog layout flow? You people can note it down. First floor plan, then placement and matching, then base DRC, then routing, then DRC LVS, and then post layout simulation. What is this post layout simulation? Post layout simulation, I will tell you what is post layout simulation. Suppose this is an inverter, right? Suppose this is an inverter. So it should get an output like this. If I give input 1 0 1 0 1 0, output should be 0 1 0 1, like that output should be like 1 0 0 1. Make it inverted. If I give 1 0 0. So why we are making the layout? Because ultimately the design cannot be fabricated. You will get schematic from the designer. Analog design engineer will give you the schematic, but this design cannot be fabricated. We need to go for the post layout simulation. For post layout simulation, what we need to do? There will be some this kind of this layout. We need to run again simulation. After simulation, we will run the simulation. Two data, this layout, this data, this waveform, this design waveform, and this simulation waveform, like after layout simulation waveform, should be exactly matched. Then only it will be called as a perfect layout. Otherwise, your layout is not good. If it is not matching, suppose that delay can come, right? For the routing parasitic, delay can come. So there, this is not acceptable. So you need to do the perfect layout. Otherwise, what is if it is this design is not matched, this simulation result is not matched, then your manager will call you and tell you that your this specs is not matching. You have taken 7 days to make this layout, and now your design is not specs is not matching. So they will give you rework, and this is a waste of time. Initially, they will 1 or 2 times they will allow you to do, but when you will have it able to project, no one will entertain this kind of thing. So make sure your layout should be quality. Like we need to maintain the quality of the layout. We need to think each and everything. That our main job is to doing layout is not just to do this randomly connection and do the placement. Layout is all about this simulation result should be matched. That's why we are doing layout, because this layout is going to fabricate. Fabricate means the chip will be fabricated. Right? This layout, this design will not be fabricated. Layout, whatever as a layout engineer we will make, this will be fabricated. So we need to maintain the quality of the layout so that it both simulation result and layout result should match. So this is the basic introduction. Anyone has any doubt? Prem Kumar, Abu Talha, Sunil Sawant, Partho Sarathi. Feel free to ask doubt, because our job is to clear your doubt. Because if you, I don't want to you people go leave the class with doubts. You came here to clear your doubt, right? And we are here to clear your doubt. Any doubt, that students? Okay, next. Assuming you people don't have any doubt, so moving to the next slide. You people can just request, just note it down as of now. Later we will start the full-fledged course, maybe whenever next week or whenever. Then I will start the what is the exam starting from the fabrication. This is just a basic introduction of the level. So now what is floor planning? Suppose I will show you what is floor planning. Suppose this is an op-amp I made. Everyone know current mirror, right? Or op-amp based thing about current. We know what is current mirror. So see here, how many devices are there? 1, 2. 2 devices are there, right? So because of these 2 devices, we are going for floor plan. Okay. So this is the reason we are going for the floor plan, because I need to. These are the devices need to place. These are the devices. 1 device, 2 devices. These 2 devices I need to place. Like this, I need to do. There is matching technique is there. I will tell you later, maybe AB pattern and all. As of now, just I am showing you the basic idea. This is what I need to place, and there is some DRC support. It will ask this to this side to this side. It is asking 0.225 DRC. So that's why I'm maintaining 2.265. Okay, like that I am maintaining. So this is what base DRC. Okay. So I will the area required to place the we will place the device. Floor plan means we will place the device on the black screen, and all the where there can be register, MOSFET, transistor, capacitor, everything there, right? Left cell, and we will clean the base gear. So this is called floor planning. Now we will go for floor planning. My floor plan done. Now there will be your lead will ask what is the area it is according. So you have to answer like how to measure the area. Suppose this area I will measure. This is 1.4. Everyone see 1.4. We'll make it full. X is 1.4 and Y is 1.5. So if I calculate, let's open my calculator. 1.7 into 1.5. Okay. So it is taking about 2.25, like 2.5 micron. Here is a micron. Here you always remember. Here is a in this screen we will everything is micron. That is micrometer basically. Yeah, micrometer. 1 micron. So I will tell my lead that 2.5 micron area is this, but he can tell me this is a too much area. You need to make the layout into 2 micron. Suppose I am taking 2.5 micron, my lead will tell no, it is more area. You need to go for the 2 micron. So I need to rethink how can I reduce the area. This is what floor planning. The floor planning means you have to place all the devices in the as much as area should be minimum. Area should be minimum. You cannot place randomly. You have to give the area should be minimum. It is the major criteria. Area is the main criteria. Because day by day, chips are getting smaller, transistor are getting bigger, transistor are getting more. Suppose if you saw previous days chip, like 10, 20 years ago, there was very big chip. Nowadays, chips are fitting in our mobile and there are billions or trillions of transistors there. So basically, chips are getting smaller every day and number of devices are getting increasing. So area is the main concern. You need to fit all the devices in the given area. Because someone will plan for the top block. Like there will top block and sub block. Someone will be the lead level or principal engineer will plan the top block and he will assign the area and you have to feed the device on the area because he already fixed the device. Then we will go for the place. Suppose if your lead has give you a 2 micron area, like that I show you. Here, your lead give you the 2 micron area. So now somehow I do some refloor plan and I make it a 2 micron area. So I will show him, sir, I can adjust it in the 2 micron. So he will tell, okay, it's good. Now we proceed for the placement. Then I will go for the placement. These are the, suppose this is the one device, I will show you. This is one device, right? Suppose this is one device. See, this is the view of our device, right? This is what I draw, right? See, this is the view of the device. This is called offside diffusion. This is called poly, which is gate. And this is called source. This side source, this is gate, source. It's not gate. See, this red color is offside diffusion. This green color is poly, which is gate. And the blue color is source and drain. Okay. So we need to place the device. Somehow I will place the device in the given area. Suppose I will place the device in the given area. Now my floor plan is done. Now I will do the placement. I will place the devices one by one. I will. And while doing the placement, you need to make sure DRC, base DRC should be clean. Okay, base DRC means this distance I told you, right? This distance. This poly to, suppose this is the angle, right? This distance or this poly to poly distance, suppose I can show. Let me turn on the poly on. This is poly to poly, there will be some distance, right? Say 0.1. It will ask 0.1. Poly to poly distance as per DRC rule. When you will run DRC, you will get to know. This poly to poly distance will be 0.1. So it is need to clean, right? So that is what my concern, and this is weight DRC. Now I will go for the after base DRC clean. There will be some concept called matching. I will not tell what is matching now. I will just tell you what is matching. Very basic idea of the matching, because matching will take 2, 3, 4 class. Matching itself is a very big topic. So just for the placement, there can be if I place the devices, suppose there will be A, B. So suppose 2A and there will be 2B multiplier, right? So I will place instead of 4 device A, B, B, matlab A device and B device. Suppose A, B, B means how can I show you this way I will tell you. Suppose this is A device, this is B device. And this device are 2 and this device are 2. And this is BB, right? So instead of going to ABB, I will go ABA. Like that I will do. Okay. AB, I will go. This is called one interdigitization matching. I will tell you what is there. So before that, I will just need to go through this matching topic when I will tell you that time. So in this way, we need to do the placement and basic thing. We need to go for the math. So there are two type of matching. One is interdigitization and one is common sense. Right? So when these are the two devices, right? Two devices can be placed AB fashion. This is called interdigitization. This matching called interdigitization. Interdigitization. And there will be another matching AB and BA. If I place it, see A, B, and BA, or BA, AB. So if you can see these two as a common, each device has common centroid. That is this. These two devices has common centroid. So you need to do this fashion like this. Okay. You need to do the matching like this ABB. So in this way, we can make the common centroid matching. Each and every device should have a common centroid. This is called common centroid matching. So what is the difference between interdigitization and common centroid? Basically, interdigitization we can go only in x-axis. We're going only in x-axis, right? But common centroid, so you can see, we can go in x-axis as well as y-axis. Same here, x-axis, this is y. This is what interdigitization and common centroid. So just it's a very basic of the matching, but don't worry, matching will itself take 2-3 class as I told. When we will teach the matching, that time I will tell you. So after matching, I will go for the base layers. So now, what is base layers? This is the most difficult typical question. What is base layers? Base layers is very essential step of analog layout, which is before routing. See, as I told you, here, suppose I will place this device. I will show the inverter layout also. So don't worry. These are the devices I need to place. I'm placing, this is the device. Now here we will get the layers, right? layer. Suppose this is poly layers. Okay, if I turn on the poly layer, and this is the N plus. This is the N plus layer, poly layer. So, as per the DRC, this is N plus layer, this is poly layer. So as per the DRC, you need to give the sufficient distance between N plus and poly. N plus to N plus, this will ask some DRC distance. Suppose it is asking 0.25. I told you, right? N plus to N plus, there will be 0.25. There will be P plus layer also. And poly to poly, it will ask 0.1. I need to give that. Okay. So this is called base DRC. These are the many, there will be N well to N well, there are many layers of N well to N well, N well to P well, P plus, P substrate, there will be many layers. So these are the things you need to take. So this is base DRC. So this is N well to N well, P plus to P plus, poly to poly. These are the distance I need to give. So this is called base DRC. Then while clearing the base DRC, we need to clear all the base. There will be, this is DRC window. When we run the caliber, then there will be DRC window. We need to clean the base DRC. Okay. We need to clean the base DRC. That time we will clean the base DRC. Like first we will, whatever base DRC will flare, this window will come like caliber. There will be a tool, caliber tool. I will, then caliber tool, we need to clean the base DRC. Then after then we will go for the routing. Suppose these are the metal. I told you, right, what is how to do the routing. Suppose, see, these are the metal I have done. See, these are the poly. These are the source line, and I connected this to M2 metal. There will be M2 metal. There will be, we need to route with this kind of metals. We need to route with, suppose this is my one device. Suppose I will show you in front. And this is my one device. So these two, there will be source, this source to this source will be connected, right? So I will take M3 metal to connect this to let this letter to be M3. Yeah, to connect connector. And one more thing, via. Via. What is via? Via means to connect the metal. To connect the metal. To connect the metal. I will use via. Okay. So this is M1. Suppose this is M1 and this is M2. Right. Suppose this is M2. And this is again suppose M3. Right. Suppose this is M3. I will show you paint that will different. I will use different color that will be the reason. Suppose this is M1. Okay. This is M1. This metal I will take as M2. This is M1. M2. And this can be also M3. Suppose let's take M3. This is M3. So to connect M1 to M2, we will use via, right? So here I will take one via. There will be M1 to M2 via. Okay. Here it will be M2 to M3 via. Like that. So basically what we will do, metal 1 to metal 2 we will use to connect metal 1, metal we will use via. Metal 2 to metal 3 to connect we will use via. Like that we need to use the vias. Okay. So these are the things. So we need to connect the via. there is one more concept, that is contact. I will show you what is contact and I will teach what is contact. See, in this class, whatever we will do using practical. There will be no theoretical. It should not there. I will not teach any single thing. I can teach you the theory, right? I have PPT. I can simply teach you the PPT. But whatever I am doing, I am showing you the tool. That is the best part of this course. Like each and every topic, if it is a very small topic, I will show you the tool. I will not show without tool. So this is C, right? I will take this. C. This is N plus diffuse. This is the oxide diffusion. The red color is oxide diffusion. Anyone unmute? Anyone? Yeah, anyone want to say anything? Hello.
No, it's okay, sir. You can continue. Also, my name is Shubhashish. Also, sir will be taking the classes. Also till 12 nanometers. So we will be teaching over the course. We have ranging technologies from 180 nanometer till 5 nanometer. Okay.
Yes.
I tell you, the class will happen mostly in 28 nanometer because planar is needed to understand. Then 16 nanometer, 12 nanometer, which is a FinFET 16 and 12, and 5 nanometer technology. What actually is good in this course is you will get exposure to the Cadence tools also, as well as the Synopsys tools also. Why? Many companies nowadays are also preferring Synopsys tools because or a mix and match combination between CAD and Synopsys both. Okay, so for a different causes, everyone's different idea. So we have to prepare you guys over both of them. So 5 till 12 nanometer, we will be using Cadence tools. We can use Synopsys also, no problem, but Cadence is more used in the market. That's the reason we are putting more effort over the Cadence. Till 12 nanometer, fully Cadence, any technology, 5 nanometer especially, because the kit for the 5 nanometer is for Synopsys. That's the reason it's good to go for the Synopsys and learn that one also. So 5 nanometer, we will be teaching Synopsys custom compiler. So you get both the understanding of Cadence and Synopsys tools with FinFET, with GAFET, 5 nanometer, the GAA FET, get all around FET, okay? And as well as the planar technology at an affordable price. Okay? So it's a win-win situation for all the candidates who are going to join.
Yeah, that
Okay.
is a
Test. If anyone has questions, they can ask us. We'll happy to help them. Sir, you can continue.
okay. Thanks, Shubhashish, for the words. As I told, we have to learn the FinFET also. So in this course, you will get all the exposure FinFET as well as planar FDSY. Everything is there. 28 is FDSY technology. That is also a buried oxide layer will be there. When we will do the 28 nanometer, I will tell you.
If one moment, I think sir has already shown you the 16 and the 28 nanometer, I guess, in Cadence tools.
Yeah, 66
one moment, I will show you the 5 nanometer as well in Synopsys custom compiler. Okay. Is my screen visible? Yeah. See, this is Synopsys custom compiler tool. Same Cadence called it as Virtuoso. Synopsys called it as custom compiler. Okay. Simply, you just open it. It's 5 nanometer PDK. Okay. So there are multiple devices are available inside this one. We can generate any one like inverter, anything we can make, but it will take time. That's the reason I'm not making. We can open it. I can right click. So this is an N-type HVT device. I can open it and show it here over a layout editor. This is a 5 nanometer technology devices. Okay. These are 5 nanometer devices. You can see multiple till ME15, metal 15, it is there. Okay. Many other things will come. We will do understand some basic simulations, then full layout level techniques. We will see all these things. See, till 5 nanometer, this technology is there. So, which is a win-win situation for all candidates. Okay, you can see here how the technology, what are the layers available, and everything you will get to know in this one. Let me check if there is any design rule manual or not in this one. Yeah, there is a process data book. Okay, for 5
Yes.
nanometer. So
Very good.
in this data book, you can get all the informations of the devices, the models, and all technology understanding of the 5 nanometer. Because 5 nanometer is a very crucial thing in the market today. It's a very catchy thing. So we are only the institute in the market providing 5 nanometer access to our candidates, starting from 180 till 5 nanometer with Cadence and Synopsys, both access we are providing. You can go and understand the things, practice at your end. 7 months of full tool access, 24 into 7 you will be getting, as well as we will be getting class recording access for 1 year of the live classes, what you are going to attend, okay? And 7 month full access to all these technology tools. Okay, so for any joining and price, contact me. Subhashish Sengupta, my name is. I think you all have the phone number. I will drop the phone number in the chat box also once. 861-726-2670. 861-726-2670. WhatsApp number, call, WhatsApp, anything. We will happy to help you. This is the whole thing of the technology notes of the this device. Okay, all things are written. Because design rule manual, everything is written inside this one. Okay. So I thought I should show you the 5 nanometer as well. So you should get some interest over that one. Okay. Okay, sir, you continue, please.
Sure.
My end is over. If anyone question, let us know.
Yeah, hi sir. This is Prem.
Yeah. Tell me.
Actually, I want to know for how many years or months we are going to get the tool access.
6 months of class, 7 months of two lessons. Why 1 month extra? Technically, it should be 6 months, but 1 month extra. Why we are providing? Because see, many times candidates unable to cope up, or they don't sometimes understand the topic, or they face difficulty to complete the period. That's the reason we are providing 7 months of tool access from the date of your joining, not from the date of the class start, on the date of your joining. If you are joining in the middle also, from that date of joining, 7 months totally will be getting. Don't
Okay, okay,
confusion that, don't get confused, but it's from the date of class start, it's not, it's from the date of your joining. Okay,
okay. Got
any
it.
questions?
And yeah, whatever those 5 nanometer and 7 nanometer are there, those are TSMC only, right? Not GPDKs.
Nah. See, I tell you, 12 nanometer is Global Foundry, TSMC
Okay.
16, 40, 65 are this technology at TSMC. 28, again 40, 110, 180 are UMC. Okay, and SCL 180. 5 nanometer is one from Synopsys.
Synopsis in the sense like can I know like which company, which foundation or TSMC only?
I can.
No. I tell you. See, TSMC will never provide the 5 nanometer only for learning purpose. Okay,
Yeah. That's what the, I
they
mean,
will
my
never
doubt
provide.
actually. Yeah.
So this is provided directly from Synopsys for learning purpose.
Okay. Got it.
Synopsys also provides for learning purpose that see 5 nanometer TSMC will not provide us, or anyone it will not get. Okay.
Yeah.
7 nanometer, 5 nanometer is not accessible. If anyone having access, then they have some fabrication related things happening going in the background. That's the reason they might have given. So that reason 5 nanometer TSMC is not possible to provide. Synopsys on that case comes into picture. They provide 5 nanometer access, and 14 nanometer also they provide. 14 nanometer is also available. So why to use 14 nanometer when you have 12 nanometer to access in Cadence, right? So better
Yes.
use 5 nanometer for Synopsys. You will get the understanding of Synopsys tools also and Cadence tools also both.
Okay. Got it, sir. Thanks.
Okay.
So as you can see my screen, this is a TSMC N16 DRM. I will show you that this is N16. So this is the DRM of as said. Show you the S5 of Synopsys, and it is N16. So let me show you the layout of this.
Yeah,
Already-
in the library, in the analog library, there is there, sir. Designs of 16 nanometer.
Yeah,
Go
yeah,
in the
already,
top.
already I created the one in inverter layout.
Oh, okay.
Show them. See, this is the layout. Okay. So these are the fins. See, apart from the planar, what are the difference? This is the fins, right? Over the fins, and these are the fins lines. These are the fins. You need to place the fins over the fin grid. These are the grids that screen you are able to see now. These are the grids. You need to place the device over the grids. And there is a fin grid and one is poly grid. You need to place the poly over the poly grid. And then we need the, and there is fin pitch, right? This fin pitch to this fin pitch will be suppose this fin, suppose if I turn on the fin only, I can show you. These are the fin fetch, right? These are the fin fetch. Now you need to check this distance is 0.35. So this fin should be equal, right? 0. If I take 0.35 now, so I can show you. These fins, then only this is the able to air. So now it will be base DRC chain. Okay. Then only this fin should be equal. Then only it will be base DRC chain. And then whatever layers is there, whatever poly to poly spacing and all, we need to take it. Only it will be base DRC chain and we need to place the globe on the grid. Okay. So this is the TSMC N16. Then there are many layers: Fox PC, Pode poly, then cut poly, OD. This OD should be always continuous. There are many things are there. I will teach you one by one. Don't worry. Whenever we will do the FinFET. Okay. So these are the N16. Now, so I was there with the layout. I can close. So I was there. So this is the polytope. So these are the base DRC, right? These are the base DRC we need to clear. Then after that, I will go. I was under LVS. So what is LVS? See, LVS means. Just a second. Let's suppose LVS means what I told, layout versus schematic. So I will compare LVS tool, basically caliber tool. Caliber will compare layout versus schematic. So schematic number of devices. Schematic this is there 5 devices here, 4 devices. There should be 5 devices. Okay. If there is a 4 pin, there also should be 4 pin. If there is a 4 net, there also it should be 4 net. So each and basically what I want to say, each and every side it should be completely matched. Then only it should be LVS. Okay. So these are the things LVS it will come in the LVS. So this is LVS. Basically, there will be netlist, layout netlist that is called GDS file. What we will do, I will tell you what is GDS file. One is basically it will take, this is a tool, our caliber tool. There will layout file GDS and CT. There will be schematic file. This is layout file will be .gds. Okay. .gds. This is the layout file. And in schematic there will be. They will take the schematic file, schematic synthesis, whatever it is. This is the schematic file. This is schematic. And after the tool will itself compare those schematic and there, and it will generate a LVS report. If LVS clean, then our pass. LVS fail, then we have to check the LVS error one by. Then there will be incorrect instant, incorrect power match, incorrect device match, property error. Many errors are there. I will tell you when I will teach. As of now, just think about this. Okay. So this is the LVS. Now, what is the common LVS error? As I told, what is LVS error? LVS at two men. One is there can be short circuit, open circuit. Basically, shorts. I feel. Suppose first one is LVS error. What are the LVS error we will get? There will be short and short circuit. Short circuit error. Suppose you have routed, you have done one routed. This is M1. This is M2. This is X net X. And net Y, it should not be short, right? But mistakenly you have routed with M2, and this M2 and M2 get sorted, right? But these are different net. So it should sorted. What is open circuit? Open circuit means suppose this gate, you forgot to connect this gate. Like there is a, suppose there is a, where is the this is the gate. This all need to connect, right? You forgot to connect this gate. So this is open circuit error. Then there will be missing devices, extra pins, pin mismatch. Then X label. Now you need to add the labels of the pins. Extra device can come, or extra mismatch of the device. All the things, the routing. There can be some other net, whatever net is this schematic and layout. This net can be mismatched. Okay. So these are the errors in common error in LVS. So we need to fix. And while clearing LVS, we have to very patient. We have to very patient. And there are some advanced topic. So when we will do in the class, one by one I will do. So these are the our course outline. So next, when we will start the full course, start with the basic CMOS fabrication. So after fabrication, we will go for the basic concept of layout, placement, routing, matching. First, after basic fabrication, we will done some basic layout, inverter and NAND, not those we will do. Then we will go for matching. So these are the outline I am giving. So matching, we will learn all the matching techniques. Then we will do some layout of current mirror, op-amp, and that differential pair, where matching and critical routing and required. Then we will till that time it is a very basic, very basic like ABCD of the layout. So we will cover this. Then we will do for the EMIR, antenna effect, latch up, crosstalk, deep well, well proximity, XTI, short channel effect, LOD, so standard cell memory layout, and then we will go for the projects. All the projects we will go, VGR, op-amp, LDO. So these are the ADC. So these are the projects we need to cover. So this is the overall course outline of our institute. So we will do one by one. As we will eventually we will do the doubt clearing session will be there. Weekly class, after the weekly classes, we will do the doubt clearing session. We will take whatever doubt you have, feel free to ask. And slowly we will start with the planar technology. Maybe we will do first to make you familiar. First we will do the tool training. This is the tool, right? So first we will go for the tool training. This all the whatever this, what is this, what is this, all the symbols, all the signal symbols you are taking, all can have the different potential. So we have to learn those. Then eventually we will move to the how to do this routing placement, what are the shortcut, how we can do the routing in this very short time. Then we will do the standard cells. Then parallelly, basically lab session and class session will be do in similar like parallel. Where first we will do this, then we will do the standard cell. Then we will move to the current mirror op-amp DC, current mirror op-amp deep pair. And at last, after the course completion, we will start with the BGR LDO. And if any special request, if you want to learn any other block, that also we will. Okay. So this overview of our course. This is the overview of the course. Anyone has any doubt? Partho, yes.
Anyone having any doubt, you can ask us.
You can take for 10-15 minutes doubt clearing session.
Our phone number is also given. 861-726-2676 in the chat box. Interested candidate can contact us or WhatsApp us. We will help you. Okay. Any doubts related to any topics or anything? Any modern tape out skills? No, tape out skills in sense what exactly? Can you tell, Sunil? Hello, Sunil.
Yeah, tape out means after the Gerber is generated, the GDS2 file is generated. What happens
Mhm.
after, and what are the steps till we get the after the GDS2
Okay. Got it.
file,
Got it.
till
So
we get the chip in hand.
I got it. See, in CMOS fabrication, we will be teaching this one. So what is the thing actually? When you design the things, you generate, suppose in a PCB, we generate Gerber files, right? Gerber files means what? It gives a layer by layer information, right? Top layer, bottom layer. I'm taking about a dual-sided PCB, okay? Top layer, bottom layer, then solder mask, silk screen for top bottom both, then drill pad holes. These are all the Gerber files information, correct, for the PCB.
Yes, correct. Correct.
Same in GDS file. When we do the fabrication on a substrate, there are different layers: substrate, then oxide layer, then gate layer, then top of that one contact metal layer, oxide gate layer, then diffusion layer, then contacts, then metals, 1 2 3 4, going on. Like a building kind of structure: one first floor, second floor, third floor. So all these floors information are called the layers information are present in the GDS. That is sent to the fabrication, and that is fabricated one by one, layer by layer uh, over the wafer by the lithography technique. Okay, and one process done, lithography, it is washed out using chemical leaching. Again, next step is done. Like this, step by step, it carries on. This is the way actually this happened. This will be taught in the CMOS fabrication. I think in the layout concept, CMOS fabrication was given. It will be taught on that one. But practically making a tape out is not possible because it's a minimum of 180 nanometer. If you go for a SCL, okay, it's a minimum cost. It will be around for you a basic. I'm telling you 4 cross 4 mm square, which is 35,000 rupees per mm square. I think 1 lakh 40, roughly 4-5 lakhs it will cost you to get it fabricated from ISRO at 180 nanometer. If you go for 7 nanometer, 5 nanometer, then it's almost 20 CR, 30 CR for a basic chip design.
Okay, so expensive.
Too much expensive. TSMC 5 nanometer, if you go and ask them, they will be charge you at least, I think, 3 or 4 million US dollar for that one.
Do they have the technology SCL?
SCL 180 nanometer is available. We have a signed NDA also. So we have already there. We can get it fabricated. Okay. So we are using for it our own, not for the course purpose. So, but if you want to get it fabricated, you can contact ISRO, SCL separately, and you can ask them. They charge 35,000 rupees per mm square. So minimum 4 mm square water value is there. So you calculate it's 1,40,000 after testing another 4-5 lakh. You can get it fabricated.
Okay. Understood, sir. Understood. Thank you.
Okay. Okay, then if no one has doubt, then we can end the session today for here and hope to see you soon in the class.
Okay, students. Nice talking to you.
Okay. Bye, everyone.
Okay, bye. Have a
Bye.
good day.